To round out this topic, our next speaker is Alan Stern, and he'll be speaking to us on the heliocentric dwarf planet population and heterogeneity in our solar system, with speculations regarding dwarf planets and extrasolar planetary systems. So whenever you're ready, go ahead.
Great. There you go. Good morning, everyone, and thank you to the organizers. This is really a great conference. I'm very happy to be here. Hopefully you'll find this an interesting topic and a little bit different from some of the other things that have been talked about. What I want to cover today are 5 topics, so it's going to be in rapid succession. First, I'm going to talk about the known dwarf planet population in our solar system. Specifically, I'm going to restrict that to the heliocentric dwarf planet population. Secondly, I'm going to talk about Pluto, Ceres, and Triton as very different examples of the way geological expression works in dwarf planets. Then we're going to talk about various axes of heterogeneity that we see in the dwarf planet population. Fourth, we're going to talk about evidence, forensic evidence, that the solar system once spawned a much larger population of dwarf planets than we see today, and where those dwarf planets are now. And then some expectations and speculations on my own part regarding extrasolar planetary systems and dwarf planets. Let's jump right in. So first of all, these are the known dwarf planets of our solar system that orbit the sun. There are 15 of them here. You know, there was a real revolution when the Kuiper Belt was discovered, because we not only discovered the third zone of our solar system, rewriting the sort of geography of the solar system, but then we began to discover Pluto-like objects that we call dwarf planets, large objects in hydrostatic equilibrium that are generally round, and that turned out to be the most populous class of planet in our system. These 15 objects outnumber the classical 8 planets, both the giant planets and the terrestrial planets, for example. And even from this graphic, borrowed from Wikipedia, it's a pretty good source. You can see their brightnesses, their albedos are highly different. Some of them have satellites, some of them do not. They have different colors, different shades of red, for example, or reddish. And so we can already see that this population is not only larger than the terrestrial plus giant planet population combined, but additionally that it's heterogeneous. On the left is Pluto, in the center is Triton, on the right is Ceres. Let me tell you why I included Triton in this sample. It's the only 3 dwarf planet objects that we have sent spacecraft to, so we have good high-resolution data on each. Triton is in a retrograde orbit around Neptune, which of course is the hallmark of its capture. It was formerly a heliocentric dwarf planet. And these 3 objects have very different geologies. They have different atmospheres. In fact, Ceres doesn't have an atmosphere, Triton and Pluto do. They have different ranges in topography, different surface ages from one another, different styles of geologic expression, different differing degrees of volatile transport, differing compositions. These 3 worlds suggest that as we go to the other dwarf planets, we should expect to see a lot of heterogeneity in their geology and their geological expression. And I look forward to missions to more of these objects, but even by astronomical techniques, we can see that that story is already holding up in a whole variety of axes. I spoke to you earlier, just a few minutes ago, that we see different colors. We see a wide range of albedo expression. We see a wide range of compositions, some with super volatiles like molecular nitrogen, methane, carbon monoxide on their surfaces, others with relatively involatile surfaces, primarily water ice, and we see a wide range of densities as well. So in every axis that we observe these bodies, they are a diverse group. I'll continue that because you can look at the satellite populations of the dwarf planets as presently known, and of course it's limited by various selection effects, but even from the data that we have, from Pluto on down, you see different architectures of satellites, different numbers, different distances relative to the Roche lobe, or if you prefer, to the Hill sphere. And so again, we see this kind of diversity, and the same in their rotation rates. In every respect, the dwarf planets form this very heterogeneous set. In fact, my claim and my suggestion to you is that the dwarf planets are every bit as heterogeneous as a group as the terrestrial planets, which you see here with another illustration for fun taken right off Wikipedia. Venus, Earth, Mars, and the Moon, Mercury, are very different from one another. And a little bit surprisingly, perhaps, but maybe not, the dwarf planets are at least as diverse as seen in our solar system. Now, moving to another topic, we expect to discover more dwarf planets as we can look deeper and deeper and further in our solar system. That's a tough problem because detection is like r squared on r squared, so it's r to the fourth. But there's interesting forensic evidence in our solar system today that there were formerly a very large population of dwarf planets that were formed. Some of this work I was involved in a long time ago, and I want to talk to you about it for just a minute. You know, Pluto is actually a double planet. Pluto-Charon is a system, which all evidence points to a giant collision, very much like the formation of the Earth-Moon system. So you might ask yourself a question: in that giant Kuiper belt, with all these things rattling, with Pluto and Charon and rattling around, what are the odds that they would collide with each other? Turns out if you do that calculation, it's very improbable. In order to make it probable, you need a large number of progenitors, or dwarf planets. The same is true for the capture of Triton. The same is true for the tilting of Uranus and Neptune by impacts. All three of these lines of evidence quantitatively point to a formerly large extent population of dwarf planets, approximately 1,000. And in fact, work done by Scott Tremaine and Paul Weissman and others shows that most of these objects would have been ejected to the interstellar medium by the clearing of the giant planet zone, or ejected to the Oort cloud, but only with about 10% efficiency, plus or minus, to the Oort cloud. 90% or so went out into the galaxy through the scattering processes. More recently, there are other lines of evidence for this as well. And some work that David Nesvorny has done and published both in 2016 and then updated in 2018 shows that we couldn't capture Kuiper belt objects into the resonances that we see them captured in the right proportions unless there was a grainy kind of migration of Neptune that requires these grainy impulses from large numbers of Pluto-type dwarf planets. So further evidence for this formerly large population that's now primarily been scattered a little bit to the Oort cloud and a lot into the interstellar medium. So let me go to my summary. Over a dozen heliocentric dwarf planets have been discovered. All but Ceres are in the Kuiper belt. We expect to find objects farther out in the scattered belt and eventually in the Oort cloud as our techniques get better. The population that we see is significantly heterogeneous in every known observational axis. And there are multiple lines of evidence that there were once 1,000 or more dwarf planets produced by the solar system, 90% of which were ejected by the giant planets to the interstellar medium. Yet about 100 or so should be available for discovery in the deeper reaches of our solar system. Finally, some speculations about dwarf planets around other star systems. I think it would be reasonable to expect dwarf planets to outnumber larger planets in many kinds of systems. I think it's reasonable to expect that significant populations of dwarf planets may be found in their Kuiper belts and Oort clouds, particularly for solar system architectures like our own with cold Jupiters. And then finally, it should not be surprising to find a high degree of heterogeneity in the properties of dwarf planets in other systems, just as we find here. Thank you very much.
Questions for Alan?
This is great. It's going to go straight into my class. Thank you so much. One follow-up remark and one question. So I was just looking at your number, the number of Jupiter families, the numbers of Plutos. So it looks like that if by the time we get to our millionth interstellar comet, we will finally get a Kuiper belt object from another system. We got 3 for now, so it may take a while. And the second one is, does this heterogeneity also extend to their interiors? Because for the larger planets, that's of course the major difference, having a core, being frozen over, having tectonic activity. And I don't know how much we know about that.
We know less about the interiors of these bodies, but we do have evidence that some of them, at least, Pluto and Triton, for example, are likely to have interior liquid water oceans. And then others with higher densities, which have much less water ice in them, probably do not. But we really need to get to the stage of exploration where we have orbiters and can really probe the interiors, which we've not yet been able to do. Question in the back?
Hi, Shubham Kanodia, Carnegie Science. Thank you for the really interesting talk. My question is, so the prediction is that there should have been thousands of these, or maybe 1,000 dwarf planets. Do you have a sense for how that compares with planet formation synthesis models? Do they also predict numbers of this order for these size planets?
Yes, in fact, that's a really good question. And I should have brought that up through the slides, is that the forensic evidence that we have, that is the clues scattered around the outer solar system for a formerly large population of dwarf planets, is supported by modeling of planet formation that has large numbers of dwarf planets formed on the way to the larger planets in the middle solar system where the giant planets are today.
All right, unfortunately, that's all the time we have for questions. Let's thank all the speakers, thank Alan and all the other speakers in our session.